So am I audible? Can you please respond? Can any one of you just let me? Okay. So wait a second. I hope my screen is visible. So in the last class, if you remember, I left one question for you to try yourself. Did anyone try? Hello. Am I audible? Okay. So in last class, I left one question for you to try. Let's discuss that again. That was question number 3 of tutorial 1. It said that let n greater than equal to 1 define phi nx is equal to 1 when x belongs to minus into n, 0 when x belongs to r minus minus n plus 1 to n plus 1, n plus 1 minus x when x belongs to n plus 1, and n plus 1 plus x when x belongs to minus n plus 1 to minus n. For every x in R. Let f belongs to BUCR, which is the space of all bounded and uniformly continuous functions. Defined on R. Then it said that whether the following is true or false, the sequence it says that the sequence phi nf converges with respect to sup norm. That means we have uniform convergence. If you remember, in the last class we had discussed that this sequence of functions phi n will not converge uniformly. So solution, we had seen in the previous tutorial that phi n does not converge uniformly. Now, if phi nf converges uniformly for every f in BUCR, this implies phi n converge uniformly. Why? Because the constant function 1 also belongs to the space of all bounded and uniformly continuous functions. But this is a contradiction. Therefore, the above statement is false. Therefore, it is false. Is it clear? In the last class, if you remember, we had proved how this sequence phi n does not converge uniformly. It cannot converge uniformly, and that will help us to give an example such that this sequence does not converge in soup norm. So, is it fine with everyone? Can you at least write in the chat box? Is it fine? Okay. Okay, then let's move to the next assignment. I hope you must have seen the assignment for quiz 2 that has been uploaded, which is not included in your evaluation part. So we will be discussing that assignment. So firstly, we have some true false questions. State whether the following are is true or false. So first one, let A be an n cross n matrix where n is greater than equal to 2 with real entries which defines a we all know that a matrix always defines a linear transformation. Also conversely, when we have a linear transformation defined on Rn finite dimensional spaces, it corresponds to a matrix which defines a linear transformation A from L to N to L to N. We know that Ax is equal to A of x is equal to A times x for every x belonging to L to N, and this is the space Rn with the 2 norm, where this 2 is summation mod xi square I from 1 to n to the power 1 by 2. Okay, this is a linear transformation. Let lambda belonging to R be an eigenvalue of A, then mod lambda should be less than equal to norm by. So I hope you remember what do we mean by eigenvalue. We are given that since lambda belonging to R is an eigenvalue of A, this implies there exists some non-zero vector x in L to N such that Ax is equal to lambda times x. We need to show that this lambda, modulus of this lambda is less than equal to operator norm of the linear transformation A. So we know that this norm is equal to supremum of norm AX L2 norm, because AX is in L2N, by norm X L2 norm for all X belonging to this space L2N minus 0. So X for all non-zero vectors. Now this, if I take Y is equal to X by norm X, where X is this X, this implies clearly Y is non-zero. This implies norm A will be greater than equal to norm of AY by norm of Y, which is equal to norm of AX by norm X. This is L2 norm by, what is norm Y? Can anyone tell me what is norm Y? Norm of Y? 1. It is a unit vector. This is 1. Now, since A is a linear transformation, this is 1 upon norm x2 AX. And since X is an eigenvector, this is lambda times X. So we have 1 upon norm x2 norm of lambda X. And we know that by the property of norm, this is lambda modulus lambda times norm x2 by norm x2. This gets cancelled out. This is equal to mod lambda. Therefore, we have modulus lambda less than equal to norm A. Therefore, our given statement is true. Is it fine with everyone, this proof? Please let me know if you have any doubt in any of this step. Here, we have proved that if lambda is an eigenvalue of a matrix A, then modulus of lambda is less than equal to the operator norm of the operator A, that is corresponding to the matrix A. Okay. Question number 2. Let W is equal to W1, W2, and so on be a bounded sequence of positive real numbers define dW from L2 to L2. Now L2 is the space of all sequences such that summation xi square is finite. We define dW x is equal to x1 W1, x2 W2, and so on. For every x, which is a sequence x1, x2, and so on in L2. They are saying that then the operator dW is invertible. So can anyone just guess whether this is true or false? Will it be invertible or not? So also my guess is also no. For that, let's look for some example. If I take W to be the sequence 1 by n, and if suppose we can find, let if possible, the dw inverse from L2 to L2 exists. In that case, we should have dw inverse times dw of x is equal to x is equal to dw of dw inverse at x. That is the basic property of the inverse. So this tells us that from here we can see that x1, x2 and so on is equal to w1 times dw inverse x. Now dw inverse x is a sequence, x is a sequence in L2, dw inverse sends this sequence to the space L2. So dw inverse x is a sequence. I take its first element as subscript 1. So the second element would be, because we are operating dw on dw inverse x. That means for each element of the sequence, we will be multiplying the corresponding element of the sequence w. So this is w, dw inverse x ka second element, and so on. So this tells us that wn times dw inverse x ka nth element is equal to xn. So dw inverse x ka nth element would be xn by wn. Now what is wn? Wn is 1 by n. We had taken it to be 1 by n. So this is n times or we can say that, sorry.
Ma'am,
Hmm?
on the assumption of the Wn is arbitrary or it is taken for
Sorry.
Wn as a 1 by n taken
Hmm. Hmm.
is arbitrary or it is purposefully taken.
I
You
have
can.
I have I have taken it purposefully in
Okay.
order to get a contradiction. I am saying that its inverse will not exist. So I have taken this specific W. I am saying that if dw inverse exists, then I should lead to some contradiction. Okay.
Okay.
So I have taken this W. With this W, suppose dw inverse exists. And if dw inverse exists, then we should have something of this form. Xn equals to Wn times dw inverse x at n. Hmm. So this is n times xn. Now we were saying that dw inverse x, this should belong to L2, then only dw inverse will be well defined for every x in L2. Here I take x to be the sequence 1 by n to the power 3 by 2. Will it belong to L2? the sequence X, is it or is it not in L2?
Not.
Why? This is summation 1 by n to the power 3 by 2 whole square. So this is summation 1 by n cube. Is it finite or not? It's finite, na?
Finite. Finite.
It's finite by P series test. So therefore, this will belong to L2. Now, since dW inverse was well defined, we should have dW inverse X should belong to L2. But see, summation n from 1 to infinity dW inverse X nth element square is equal to summation n from 1 to infinity n xn ka square from here. And what is xn? This is summation n from 1 to infinity n by n to the power 3 by 2, which is summation n from 1 to infinity 1 by n. This is never finite. From here, we get a contradiction. Is it fine?
Yes, ma'am.
Therefore, our statement is false.
Hi Nidhi, I have one question. My argumentation was slightly different.
Hmm.
So what I was thinking is like I can take omega and its first term could be 0,
Okay.
and there would be multiple L2, there will be multiple elements in L2 which will have just
So
one
you
image.
have, wait a second. So you have taken W to be any sequence such that the first term is 0
Yes,
and rest
and
of the terms
rest of the terms could be what with the such that the infinity subnorm is less than
finite.
infinity. Yeah,
Huh.
and I can show that there will be the pre-image of one element would be multiple elements. So I think would this argument work or not? I was
So,
thinking.
so you are saying that corresponding to this dW, if we had dW inverse
Yeah,
L2 to L2, in that case, for some element here, you are
yeah,
getting more than one pre-images.
yes.
That's fine, na? Even for constant function. See, if we have a constant function f from R to R, so f inverse of 1, suppose f is constant 1, so f inverse 1 is whole of R. We have more than one pre-images. We can have more than one pre-images.
But would this be called as a, I
No,
mean,
I don't think that.
invertible? If would be called as invertible?
Oh, invertible. So for invertibility, we need onto as well, na?
Yes,
One and onto. So
one one and yeah,
this won't be 1 in that case.
yeah.
Yeah, yeah. Yes, in that case you can say. Hmm. So
Okay.
so you are showing for dW itself, na? For
Ye-
dW,
Yes. All I'm
uh,
saying,
we are,
it's
you are
not
show,
on. Yeah,
you are showing that this dW is never, it can't be 1.
yeah.
Yeah. That's good. You can do that. So I hope my procedure was fine with everyone. I took a specific W, and corresponding to that, I have shown that dW inverse cannot exist. Let's move to next question. Let Fn be a bounded sequence in C01 with sup norm assume that first thing Fn is a polynomial of degree less than or equal to a. Second thing, norm Fn infinity is less than equal to 1, and these both are satisfied for every n in n. They're saying that the sequence admits a convergent subsequence. So can anyone tell me what result we can use to show that a sequence has a convergent subsequence? So in R, you must have read under some circumstances, a sequence has a convergent subsequence. A bounded sequence has convergent subsequence. When do we say that?
When the sequence is Cauchy.
Yeah, I'm asking about the result. If you remember the Bolzano-Weierstrass theorem, it says that every bounded sequence has a convergent subsequence. So similarly, for we have a theorem for continuous functions as well. Can anyone tell me what kind of result theorem we have that states that a uniformly bounded sequence might have a convergent subsequence under some circumstance, some conditions? So, do you remember Arzela-Ascoli theorem? Ascoli-Arzela theorem. Are you familiar with it?
No, please state the statement.
Okay, I'll just recall it. Let's recall. It's a very nice theorem. It's used a lot at a lot of places. This is Arzela, Arzela, Arzela-Ascoli theorem. Statement. Consider a sequence Fn of continuous real valued functions defined on a closed and bounded interval, defined on some interval of the form AB. If this sequence is uniformly bounded and uniformly equicontinuous. Then there exists a subsequence Fnk that converges uniformly. So the main important terms that you should be aware of while using this definition, this theorem is uniformly bounded and uniformly equicontinuous. So can anyone tell me when do we say a sequence is uniformly bounded? Hmm? Uniformly bounded. So a sequence Fn is said to be uniformly bounded if there exists some constant such that mod Fnx is less than equal to m for every x in AB and for every n in N. Or we can say that the sup norm Fn infinity is less than equal to m for every n in N. The next term is uniformly equicontinuous.
Ma'am, why it is called uniformly?
Uniformly because this is occurring for every x in A to B. If you remember, uniform convergence, in uniform
Hmm.
convergence, we have that epsilon does not depend on x. That
Okay,
means
okay.
epsilon and delta, they were fixed for all x. Similarly,
Hmm.
here also this constant is fixed
Hmm.
for all x. That is why
Hmm.
we are using the word uniformly. So
Okay.
next is uniformly equicontinuous. A sequence Fn is said to be uniformly equicontinuous if, again, for epsilon positive, there exists a delta positive which is independent of n and x such that mod fnx minus fny is less than epsilon whenever mod x minus y is less than delta. Again, here also our epsilon and delta are independent of x. That is why we have uniform continuity. So I hope the terms uniformly bounded and uniformly equicontinuous is fine with everyone.
It is similar like a Cauchy sequence, Cauchy convergence. The condition f of n of.
Cauchy convergence in the uniform norm,
Hmm.
the SOAP norm,
Okay.
something like that we can say. So whenever a sequence, this is a very great result, Arzela-Ascoli theorem, you should remember it. Whenever a sequence is uniformly bounded and uniformly equicontinuous, then the sequence must be of continuous functions defined on closed interval AB. In that case, we have a convergent subsequence. Now look at the problem. Our statement say, yes,
Nidhi, is there a difference between continuous and equicontinuous?
of course. For continuity is a point-based property. This is for all x, y, x minus y less than delta. For continuity, we have a fixed point now. Fn x minus Fn c is less than epsilon whenever mod x minus c is less than delta. So continuity is for each point. Uniform continuity, uniform, again, yes, next comes the uniform continuity, and after that we get uniform equicontinuity.
What is the difference between uniform continuity and uniform equicontinuity?
Uniform continuity is for one function. This is for a sequence of functions.
Ah, I see. Okay, okay. I see.
This
I get it.
here,
Thanks.
this epsilon and delta are independent of n and
Any
x.
as well. Okay, got it. Thanks.
So whenever a sequence is uniformly equicontinuous and uniformly bounded, then we get a convergent subsequence. Now let's get to our problem. This statement 2 gives us the uniform boundedness. We have a sequence of continuous functions with norm f n infinity less than equal to 1 for every n. That means we have uniformly bounded sequence. If we could prove that the sequence is uniformly equicontinuous as well, then we can use the Arzelà-Ascoli theorem to prove the convergence of a subsequence. Is it fine if we prove the uniform
Yes, ma'am.
equicontinuity? Okay. So for that, we should consider the point that our fn's are polynomial of degree less than equal to k. And k is fixed. So we can write, we have fnx is equal to sum an k x to the power k plus an k minus 1 x to the power k minus 1, so on up to an 1 x plus a naught. an naught. So our each polynomial will be of this form because they are saying that the polynomial should not have degree greater than k. So the degree is less than equal to k. These a and k can be 0 as well because in for the cases where the degree is strictly less than k, we don't know. So in that case, a and k can be 0 as well, but all the functions will look of this form. Now see, for equicontinuity, we need to see this type of term. No? fnx minus fny. It will be ank x bar k minus y bar k plus ank minus 1 x bar k minus 1 minus y bar k minus 1 and so on up to an1 x minus y plus 0. Is it fine? So we all know that a bar n minus b bar n is equal to a minus b times a n minus 1 plus a n minus 2b and so on up to a b n minus 2 plus b n minus 1. I hope you remember this expression, this equality. So this gives us, this is equal to, I can take mod x minus y outside, modulus of a n k times, this is x to the power k minus 1 plus x to the power k minus 2y and so on up to x y to the power k minus 2 plus y to the power k minus 1 and so on up to an2 x plus y plus an1. Is it fine? So now you can see that since all these x and y are less than equal to 1, we were given our domain was interval, close interval 0 to 1. So each of this term will be less than equal to 1. So the sum would be eventually, this sum would be eventually less than equal to k. In next term, here we have k terms. In the next term, we will be having k minus 1 terms. Again, that sum would be lesser than equal to k and so on. So we can write this is less than equal to k mod x minus y times modulus a and k an minus 1k and so on up to, sorry, an k minus 1, an2 plus an1. Now this is equal to k x minus 1 and this is fnk at 1. And since the uniform norm is less than equal to 1, so this is less than equal to k mod x minus y. This will be less than epsilon whenever mod x minus y is less than delta, which is equal to epsilon by k. Now this epsilon and delta are clearly, this delta is independent of n and x. So we get, from here we get equicontinuity, uniform equicontinuity. So is this uniform equicontinuity fine with everyone?
Yes.
So by, and hence by Ascoli-Arzelà theorem, we get a convergent subsequence, uniformly convergent subsequence. Therefore,
One question I have regarding the mod fnk at 1 value.
this,
Yes, yes. Is it? It depends on n, right? I mean,
no, because we were given that this is less than equal to m for every n in n. That is why, that is what our uniform boundedness
okay.
was
So
telling.
we can replace it by m, right? Okay.
This yeah, this m is the statement. In the problem, it was given this is less than equal to 1 for every n in n. Fine.
Yeah.
Next question. Next we have answer the following. So we are done with true false. Number 4. Let D be a vector in Rn and capital D be a diagonal matrix with dii is equal to di and dij is equal to 0 for every I not equal to j, and this is for every I 1 to n. Basically, all the diagonal entries are given by the vector d. Now let 1 less than equal to p less than equal to infinity. Consider the linear transformation on Rn defined by, that is, D is a linear transformation from LNP to LNP, where LNP is the same as we discussed earlier, and D of x is D times x. Compute the norm of D. Can you just try it once? I'll wait for 5 to 6 minutes. So can just try using the definition of operator norm. We all know that operator norm D is supremum norm dx by norm x. Use this fact for all for p finite. Try this. Take some arbitrary element in L and P, evaluate dx, then its norm. So what's this Helder's inequality?
We can use this, no? Sorry, it won't. Yeah. Mod of dixi summation is equal to, but here it won't. We can't use. Sorry.
No. Here we need to take its power p as well.
Yeah.
We
Yeah.
need to evaluate this p norm. Just try it. So let's come see how does our dx look like. We have d from ln p to ln p, d at x is equal to d times x, which is, now d is a diagonal matrix, d11 is d1, then d2, dn, rest of the terms are 0. This times x1, x2 up to xn. So this is matrix d1, x1, d2, x2, and so on up to dn, xn. Now let x belonging to ln p minus 0 be arbitrary. Then the p norm of dx to the power p is equal to summation I from 1 to n di xi to the power p. Now this is less than equal to maximum I from 1 to n modulus di to the power p. Summation I from 1 to n mod xi to the power p. Clearly, each of the element di will obviously less than equal to maximum of modulus di. So if I take this maximum as d naught, this is equal to d naught to the power p, and this is equal to p norm to the power p of x. Now this tells us that norm dx p norm by norm x p norm is less than equal to d naught for every x belonging to ln p minus 0. Now since for each x in this set, this is less than equal to d naught, this implies the supremum norm dxp by norm xp, x belonging to ln p minus 0, is less than equal to d naught. Now if I can find a vector, some x naught in ln p minus 0, such that dxp by xp is equal to d naught, in that case we get this supremum is attained, because this is less than equal to, this is less than equal to d naught for every x in lp minus 0. If I can find some x naught where this supremum is attained, that means it is the maximum and that is equal to our norm. Is it fine with everyone that if I can find a vector x in ln p minus 0 such that this norm is equal to d naught, then our supremum will also be equal to d naught. So now see, we had d naught is equal to maximum of mod di I from 1 to n. Suppose this maximum is attained at some point j. This implies, suppose the maximum is attained at j, we get d naught is equal to modulus of dj. Now let let x is equal to ej, where ej is the vector everywhere 0, it is 1 at jth position. Now can you evaluate dej? What will be dej? dej is nothing but 0, 0. We have just 1 at jth position. This will be 0 everywhere and dj at jth position. Rest of the places it is again 0. So this will give us norm dej of, LP norm to the power p would be, or we can directly take LP. This will be modulus dj. And since norm ej is equal to 1, this gives us norm dej p by ej p is equal to mod dj, which is d naught, which was supremum of all these norms. Therefore, this is, so from here we get supremum dxp by norm xp, x belonging to ln p minus 0, LP is equal to d naught. Therefore, our norm d is d naught, which is maximum I from 1 to n modulus di. So is it fine with everyone? How we evaluated the norm of this operator d? So if you have any doubt, please let me know. If not, let's move to next question. Question number 5. Let W equals to W1, W2, and so on be a sequence, be a bounded sequence of positive real numbers. Define dw as we had done earlier. dw from L2 to L2. dwx is equal to w1 x1, w2 x2, and so on, where for every x is equal to x1, x2, and so on belonging to the space L2. If I take this w to be the sequence wn, and from 1 to infinity, where wn is equal to 1 by 2 plus 1 by k, if n is equal to 2k, and this is equal to 1 by 3 plus 1 by k if n is equal to 2k minus 1. Then for every n in n. Then compute norm dw inverse. Can you first see what dw inverse will be? We have seen earlier that for some specific w, this dw inverse was not even well defined. So can you check that for this w we can find dw inverse? Suppose it has an inverse. Let t from L2 to L2 be such that t dwx is equal to x is equal to dw dx for every x in L2. This gives us x1, x2, so on. This sequence is equal to w1 times tx का first element, w2 times tx का second element, and so on. So this tells us that wn, nth element of tx, is equal to xn. That means the nth element of tx is equal to xn by wn, which is equal to, so we have wn is equal to 1 upon 2 plus 1 upon k for whenever n is equal to 2k. So 1 upon w would be 2k upon k plus 2. So this is x 2k times 2k by k plus 2 whenever our n is of the form 2k, and when n is equal to 2k minus 1, in that case 1 upon wn is 3k by 3k by 3 plus k. So this is x 2k minus 1 times 3k by k plus 3, where n is equal to 2k minus 1. Similarly, you can see that now, okay. Now if I define sequence u, u1, u2, and so on, where un is equal to 2k by k plus 2 whenever n is equal to 2k, and 3k by k plus 3 whenever n is equal to 2k minus 1, you can see that du is actually the inverse of dw. I would like you to prove this yourself. Just take an arbitrary element in x. One side we have already seen. We have already seen this side. All you need to check is this side as well. So taking t to be du, you should get t of dw of x is equal to x. Okay, so this is our inverse. This dw is invertible. We need to compute the norm of dw inverse or du. To find, we need to find norm of du. Now let x belonging to L2 minus 0 be arbitrary. then the L2 norm of du x ka square is equal to summation n from 1 to infinity un xn square. Now I can take the even terms and odd terms separately. So this is k from 1 to infinity u2k x2k square plus summation k from 1 to infinity u2k minus 1 x2k minus 1 square. Now we know that u2k is 2k by k plus 2 square times x2k plus summation k from 1 to infinity, and this is 3k by 3 plus k square x2k minus 1 square. Now this is less than equal to, we all know that k by k plus 2 k plus 3 is less than k by k plus 2, and this is less than 1. So this gives us that is less than equal to 4 times summation k from 1 to infinity mod x2k square plus 9 times summation k from 1 to infinity mod x2k minus 1 square. So this is basically less than equal to 3 times summation n from 1 to infinity mod xn square, which is the L2 norm of x, not 3, 9. So this implies norm du x 2 by norm x2 is less than equal to 3 for every x belonging to L2 minus 0. This implies supremum of all these terms, which is actually our norm du by x2, x belonging to L2 minus 0 is less than equal to 3. Now if I find an element x, if there exists some x in L2 minus 0 such that norm du x 2 by norm x2 is equal to 3, then we will get 3 is equal to du x2 by norm x2, which is less than equal to supremum of du x2 by x2, x belonging to L2 minus 0, which is equal to norm du. From here, we will get norm du greater than equal to 3, and we already had norm du equals to 3. Then we will get the operator norm of du is equal to 3. So if we can find some x in L2 minus 0 such that this is equal to 3, in that case we can deduce that the operator norm of this operator du will be 3. Now let's see. Now since the sequence, we know that this sequence 3k by k plus 3 converges to 3. This implies for every epsilon positive, there exists some k naught in n such that mod 3k by k plus 3 minus 3 is less than epsilon for all k greater than equal to K naught. This K naught will help us to find such vector x. This gives us 3k by k minus 3 is greater than minus epsilon plus 3 less than epsilon plus 3 for all k greater than equal to k naught. Hence, 3k naught by k naught minus 3 is strictly greater than 3 minus epsilon. Take x to be the sequence xn where xn is equal to 1 whenever n is equal to, for n equals to 2k naught minus 1. So xn is 1 for n equals to 2k naught minus 1 and else it is 0. So we have just one term in the sequence 1, one non-zero term, rest of the terms are 0. So this gives us that L2 norm of this x is equal to 1 and what will be dux? So if we evaluate the nth term of dux, which is un times xn. Now this xn is non-zero only when n equals to k naught minus 1. So it is an odd position. This is equal to u 2k naught minus 1 or we have this is equal to un times 1 when n is equal to 2k naught minus 1, 0 else. And this is, we know that, and since u 2k naught minus 1, this is equal to, so u at odd positions is, where is our u? This 3k by k plus 3. So this tells us u 2k naught minus 1 is 3k naught by k naught plus 3. This implies the LP norm, sorry, L2 norm, no? We're in L2 norm. The L2 norm is equal to, since rest of all the terms are 0, we have just one non-zero term. So this is equal to 3k naught by k naught plus 3. Now we know that this is greater than 3 minus epsilon. This tells us that norm dux2 by norm x2 is greater than 3 minus epsilon. Since epsilon positive is arbitrary, we get supremum norm dux 2 by norm x2 for every x in L2 minus 0, the supremum should be greater than equal to 3. And this was our norm du. Hence, earlier we had shown that norm d is less than equal to 3. This was our equation 1. And this is our equation 2. Hence, by first and second, we have norm du is equal to 3. That is norm dw inverse is equal to 3. Is it fine with everyone? How we proved the operator norm of dw inverse? Firstly, we computed the DW inverse. We found a sequence UN such that DW inverse is basically DU. So all we need to find is the norm of DU, operator norm of DU. For that, we need to evaluate this type of terms. We need supremum over norm DU x by norm x. Firstly, using the fact that the sequence UN has an upper bound 3, we deduce that this supremum or at the end our operator norm will be less than equal to 3. And then for each epsilon positive, we found an element in L2 such that its norm would be greater than 3 minus epsilon, and since epsilon positive is arbitrary, we get the supremum is less than equal to greater than equal to 3. Hence we get the operator norm. Please let me know if you have any doubt in this question. If not, let's move to the next question. Question number 6. A part. Let A be an n cross n matrix with n greater than equal to 2 and with real entries which define a linear transformation A from L to N to L to N. L to N is again Rn with L2 norm. Show that norm A square is equal to supremum x belonging to Rn minus 0 x transpose Ax by x transpose x. I would like you to try this yourself. I'll wait for 5 to 10 minutes. Just use the definition of the operator norm, which is basically supremum over all x in Rn minus 0 of the supremum of norm Ax by norm x. Try to evaluate what norm Ax would be in terms of A transpose. I'll come back in 5 minutes. Please try this. So could anyone prove it? We claim that this is nothing but X transpose AX by X transpose X is basically norm AX2 by norm X2, and hence by the definition of this will be second. This will be square, and hence by definition of the operator norm, we will get this norm square is equal to the supreme. For X in Rn, we have Ax is equal to A is a matrix A11, A12, A1n. A21, A22, A2n, and so on up to AN1, AN2, ANN times X1, X2, so on up to Xn. So this is summation j from 1 to n A1j xj. Summation j from 1 to n A2j xj, so on up to summation j from 1 to n A nj xj. And X transpose A transpose is X1, X2 up to Xn times A11. Now we have A transpose. So this is A12, A1n, A21, A22, A2n, so on up to AN1, AN2, ANn. So this is a 1 cross n matrix, n cross n matrix. So the product will be a row matrix. First term is summation j from 1 to n A1j xj. Summation j from 1 to n A2j xj, and so on up to summation j from 1 to n ANJ xj. So from here we get X transpose A transpose, a row matrix, times AX, a column matrix. This is of the form 1 cross n, n cross 1. So this will be a singular value. And you can evaluate this is equal to summation I from 1 to n, summation j from 1 to n Aij xj square. And from here we have norm Ax, L2 norm of Ax square is equal to summation I from 1 to n, summation j from 1 to n Aij xj whole square. and this is same. Norm ax2 square. Similarly, you can see that x transpose x is basically L2 norm square. So this gives us x transpose ax by x transpose x is nothing but norm ax2 square by norm ax2 square for every x in L2n minus 0. Hence the supremum and hence the operator norm. So let's move to its second part. Part B. If U is an orthogonal matrix. So can anyone tell me what do we mean by orthogonal matrix? What special property it holds? Orthogonal matrix. For orthogonal matrix we have U transpose is equal to identity. So basically its transpose is its inverse. And if A and B are n cross n matrices, such that A is equal to U transpose B U, then show that norm A is equal to norm B. So by above, we know that by part A, we have norm A square is equal to supremum x in Rn minus 0 x transpose A x by x transpose x. Now, for every x in Rn minus 0, we have x trans or let it be. Let's write it here only. Now this is equal to supremum x in Rn minus 0. We are given that A is equal to U transpose B U. So this is x transpose U transpose B U transpose U transpose B U times x by x transpose x. And we know that transpose of AB is B transpose A transpose. So this can be written as U transpose B U. Now this is equal to supremum x in Rn minus 0 x transpose U transpose B B transpose B U x by x transpose x. Why? Because U transpose is identity. So this in between term vanishes. So this is equal to supremum x in Rn minus 0. This is transpose of Ux B transpose B Ux by, now I can bring identity in between X transpose and X. So we have X transpose U transpose times UX, which is equal to supremum Y in Rn minus 0 Y transpose B transpose B Y by Y transpose Y. Because for every X in Rn, for every Y in Rn minus 0, there exists some X in Rn minus 0 such that Y is equal to Ux, because this U is invertible. So taking supremum over the terms having Ux is equal to having supremum over the terms of the form Y. Now this is equal to norm B square, as we have done in part A. So this tells us that norm A square is equal to norm B square, and hence norm A is equal to norm B. So if you have any doubt in any of this step, please let me know. Okay, then let's move to the next question. Is my screen visible?
No, ma'am.
So now it's visible, huh? Let's move to the next question. It's part C. Let rho A be the spectral radius of A. Spectral radius of A, which is the maximum of modulus lambda, where lambda in C is an eigenvalue of A. So the maximum absolute value of eigenvalues of A is called its spectral radius. So that rho A is equal to the operator norm of A if A is symmetric. So can anyone tell me something about the eigenvalues of symmetric matrix?
They are real.
They are real. Also, we know that symmetric, so since they are real, so we are this absolute, okay, since they are real, in that case, we can use some idea from question number 1. If you go back on question number 1, from there we had seen that this modulus lambda is less than equal to norm A for any A. In this case, we have specific symmetric matrix. Also, we know that symmetric matrices are diagonalizable. So we will use that property of symmetric matrix. And question number 1. So, solution. We know that symmetric matrices are diagonalizable. And by diagonalizable, we know that if a matrix is diagonalizable, then we can find uh, a basis that contains the eigenvectors. So if I take the orthonormal eigenvectors, we can find a basis. Basically, if a matrix is diagonalizable, then we can find if a matrix of order n cross n is diagonalizable, then we can find a basis of orthonormal eigenvectors of A, and which is basis for Rn. So since A is symmetric, implies A is diagonalizable. This implies there exists an orthonormal basis is V1, V2, so on up to Vn of Rn, such that these VIs are eigenvectors of A corresponding to some eigenvalues lambda I. So now since S is a basis, let X belonging to Rn be arbitrary. Then we can write X is equal to summation I from 1 to n alpha I Vi. This gives us norm X2 I'll be taking norm 2. You can do that for arbitrary P as well. So norm X2 will be summation I from 1 to n summation j from 1 to n alpha j v j I square, where vji is the ith element of the vector vj. Okay, and ax is equal to summation I from 1 to n alpha I AVI, because A is a linear transformation, and AVI is equal to lambda I VI, because lambda I is an eigenvalue. VI is the eigenvector corresponding to the eigenvalue lambda I. Therefore, we have AVI is equal to lambda I VI. Now, this gives us the L2 norm of AX is equal to summation I from 1 to n mod summation j from 1 to n alpha j lambda j vji square. Now this is less than equal to rho a square, because rho a is basically the maximum of all lambda modulus lambda i's. So I can take this outside and this will be less than equal to rho a square. Now this is summation I from 1 to n summation j from 1 to n alpha j vji square. Now this was the L2 norm of x. So this is rho a square times 2 norm of x. So this gives us that norm ax square by norm x, this is less than equal to rho a for every x in Rn minus 0. So this tells us that our operator norm is less than equal to the spectral radius. Let's mark this as 1. Further, again, if I can find some vector x in Rn minus 0 such that this norm ax by norm x is equal to the spectral radius, in that case we will get norm operator norm equal to the spectral radius. Now we know that rho a, since rho a is maximum of all lambda i's, I is equal to 1 to n. Obviously we have n cross n matrix, so we will have n eigenvalues. This implies there exists some j belonging to 1 to n such that rho a is nothing but modulus lambda j. So if I taking x to be vj, we have norm x 2 is equal to 1 because we had taken the orthonormal basis, and avj is just lambda j vj. This gives us the norm of avj is equal to this 2 equal to norm vj lambda j vj, which is by the property of norm, this is equal to modulus lambda j times norm vj2, which is equal to modulus lambda j. This gives us avj2 by norm vj2 is equal to modulus lambda j, which was our spectral radius. Hence, spectral radius is equal to our operator norm. So is it fine with everyone? So this is it. We are left with one question. I would like you to try that. I want you to try that question before coming to the next class. In the next class, we'll start with discussing that question. Okay then. So if you have any doubt in today's class, please let me know. Otherwise, we can leave. We'll meet next Friday. Please try the last question. Even I am not able to, even I am having some confusions in that question. If you get a better solution to that problem, it will be helpful for me as well. Okay, then we'll meet next Friday. Thank you. Bye.
Hi Nidhi, just wanted to ask you one thing. Are you there? Nidhi, are you there?
Yes.
I just wanted to check if we can discuss some of the lecture material as well, because
Please
um,
let me know which lecture do you want to discuss. Please let me know today itself so that I can prepare.
no, in general, like week on week, what whenever the new material comes in, so that we can discuss like when some if we have some doubt. I don't have anything as of now, but just wanted
Okay.
to check with you if we can.
Uh,
Yeah.
See, I can try to watch all the lectures, but see, even I am doing PhD, so I can't promise that I'll watch all the videos. I'll try my best.
That is
So,
fine. I mean, I'm not asking you like I don't expect, to be honest.
uh-huh.
It's just that with the lectures, like I have tried this course like couple of times before as well. It's very dry in a way. I don't matlab,